Good afternoon, ladies and gentlemen. Welcome back to my favorite class. 3 o'clock, time for some dynamics. Rawr! Couple announcements. Number one, okay job on exam 2. You did okay. I was hoping for a little bit higher scores, but generally it was okay. Longer form problems are more prone to small errors like sign errors or directionality errors or angle errors or so on and so forth. Converting from degrees to radians was kind of a problem. Generally, the errors I saw in your work for the exam were along those lines. It was like forgot a negative sign, wrong way for the work term, forgot how to do statics in number 1, like just little, kind of just like what I would call little things. Methods are generally good, which makes me happy, though the execution of the math was a little bit suspicious. So the grades reflected that, and I'd say the average for the test was like mid-70s. And we're in pass-fail here for this particular quarter, and no one's even close to failing. So don't freak out about your exam score. Everyone's doing fine. No one's in danger of failing the class. So just keep up the good work with homework, and everyone's gonna be great. Okay. So that's exam number 2. The solution's posted if you want to take a look. All right. Next discussion point is your homework on conservation of momentum is going to be due this Thursday. It's 4 problems long, and you already should be able to do numbers 1 through 3. So the only one that you shouldn't really be ready for yet is the impact one, which is what we're going to talk about in the next 2 lectures. All right, so give that homework a crack and give it a go if you haven't already done that. It'll be due on Thursday. You're going to learn how to tip over an SUV in that homework. Very exciting. Or if you're from Wisconsin, maybe it should have been a cow tipping problem. But either way, you're tipping something over. All right. Next is your next simulation for this class is posted, and it is on a work energy of a pendulum, which is attached to a spring. It's kind of an interesting problem. It's looking at what is the velocity at the end of a pendulum given certain spring constants and certain geometries of the problem, so on and so forth. So what I have you do is sort of map out what the velocity of the pendulum is given various changes to spring constants and etc. So take a look at that simulation. That'll be due a week from today, next Tuesday. I think it's the 5th. May the 5th be with you. Oh, 1 day off. All right. Any questions? Our favorite class. Comrades, wow. Okay. Is this Russia all of a sudden? Yes, comrade, this is your favorite class. All right, well, if there's no further ado, let us do some dynamics. In Russia, great dynamics do you. Okay. All right, let's review. We were looking at conservation of momentum. And specifically, we had equations for conservation of linear momentum, which was something like the linear momentum at the center of gravity, state number 1, plus the impulsive forces, which we write as the integral of f dt, equals the final linear momentum at the center of gravity of the object in state number 2, where we remember that our linear momentum is the mass of the object times the velocity of the object. So that's your conservation of linear momentum. We also had an angular analogy, which was kind of specific for rigid bodies that have volume. And that is that the angular momentum, which we use the capital letter H for, the center of gravity in state number 1, plus the integral of the impulsive moments acting over time. So a short torque or something equivalent equal to the angular momentum of the object, state number 2, where the angular momentum can be given by either this I omega, or we also saw it as R cross V or R cross L, if you like. Same difference, all the same to me, should be all the same to you, all equivalently easy to handle. So that's your conservation of momentum. What we're going to do now over the next 2 lectures is apply the conservations of momentum equations to impact between rigid bodies. So what we're going to do over the next 2 lectures. Apply to impact of rigid bodies. So let's do that. Fortunately, or what I hope is the case, is that you have seen impact of particles. Now, impact of rigid bodies is different because rigid bodies have volume and particles do not. So particles will always sort of collide at their centers of mass because particles only have centers of mass. That's all that they are, okay? Rigid bodies are different, and that's because they don't always collide at their centers of gravity. And because of that, you can impart rotation when you have impact between rigid bodies. What do I mean by that? Okay, so here's this writing pencil that I have and I use for my writing pad. All right, I'm holding it sort of steady on the right-hand side here. Well, my right, your left. And if I were to like drop something and hit the end of this particular pencil, since I'm not hitting it at the center of mass necessarily, it's going to impart rotation to this guy. All right. And that is something that you don't see with particles because particles don't have any volume. They can't rotate because there's nothing to rotate about. So impact of rigid bodies is complicated in the fact that with this, what we call eccentric impact, we get these crazy angular velocity terms that can kind of pop into the situation. All right. So you have to think about, all right, if I drop something at the end here, how much is that thing going to rebound back? How much energy is going to be transferred to this? And then when it transfers, what's the resulting velocity at that location? Complicated, man. So we got to do that. All right. But before we do that, we need to sort of make some definitions about impact, because when we talk about impact, it's kind of its own sort of demon, and it requires its own like coordinate system and general definitions to get us there. All right. So here we go with impact of rigid bodies. All right. So let's kind of go back and start with like a general impact between like two particles. Okay. So set the stage with an example. And that is 2 hockey pucks colliding. All right. So we'll call them puck A and puck B. A has a mass of MA. Puck B has a mass of MB. They are not necessarily equal. Let's just say that they have mass MA and mass MB, not necessarily the same. All right. So initially, you should be thinking in your head something that looks like this. Here is puck A. Here is puck B. And let's say they're on a collision path. They're going to hit each other. All right. They're on a path for collision. Got a center of gravity here. Oh, geez, what happened? Center of gravity here, center of gravity here. And let's say they have linear momentums. Here, this is M, V, B. And I'll say that this is in state number 1. All right, because they're about to hit each other. Here, this is the mass times the velocity of A, state number 1. So this is their linear momentum. They're not quite hit each other yet, but they're about to. Right? Right when they strike each other, they're going to transfer loads between that point of impact through like this impulsive behavior. Right? So initial momentum was there. Then we have an impulse where they collide. So that's where they impact each other. Right? I'm not Dr. Severe. I can't draw perfect circles. Sorry. That guy's amazing with his like drawing ability. All right. Right when they hit each other, there's this like temporary pause where there's not really a lot of motion going on. Okay. You got object A coming to hit object B. They hit each other and they sort of like move into each other and then they rebound. All right. So this impact, you don't really like see anything and they don't necessarily have a lot of velocity at this point. So we'll just say that there's some impact that's happening. But we do know that internally at this point of impact, here I'll say that this is the point of impact. There will be some forces that are kind of like transferred or some forces that are occurring at that particular point. And we'll come back to that. Right? Where that point of impact occurs, the line that is normal to that particular point where those things occur is the line of impact. So let's draw that. This is line of impact. And let's give that a formal definition. All right. Here, the line of impact. Let's do it the other way. Let's give a definition first. So here, I'll say that the line of impact is the normal to the surface of contact. Contact surface is the line of impact. Or you might see it as like line of action, but line of impact is a little bit more appropriate. I'm going to kind of like shorthand it as LOI going forward in the figures, okay? So line of impact here, this is LOI. All right. Then after they sort of hit each other, they're going to rebound against each other with some final momentum. All right, so they hit each other and they rebound off each other where their centers of gravity, now kind of forcing them to move in the opposite direction after they've hit each other. Here, this is M, V, A, 2. And here, this is M, V, B, 2. Okay, where this is puck A and this is puck B. So you get the general idea. And this here looks a lot like a momentum diagram, right? So you have some initial momentum that's occurring. There are some forces that are acting. Okay, so here they're sort of internal to the system. And then you have some final momentum which is occurring. So this is like conservation of momentum, but for multiple particles. So similar. I'm not going to say similar. This is conservation of momentum. All right, so we'll just say momentum is conserved. This looks a lot like a conservation of momentum sort of diagram, right? Now this is, I've kind of drawn the most simplistic case here, where you have two objects that are moving in the same direction, right about to strike each other at a particular point. So that's sort of like the easiest that you could possibly imagine, right? We can classify these impacts using a variety of vocabulary for the what is actually happening in the particular impact. So what I'll say here is if the mass centers, oh gosh, handwriting. If the mass centers of the objects are on the line of impact, this is known as central impact or centric impact. Or or you might hear it as centric. Right? So the last example that we had is central impact, okay? So here are the centers of gravities of the two different pucks, right? There's center of gravity A and there's center of gravity B. Their centers of gravity lie on the line of impact, okay? So it's central impact, all right? Otherwise, if it's the situation where the center of mass is not on the line of impact, then you have eccentric impact. Otherwise, you have what's called eccentric impact. Right? So let's look at some examples of this and what I mean by eccentric versus centric impact. Okay? So centric is like your particle collision. All right, so this is your pucks hitting each other. Puck number 1 hitting puck number 2. Here we are. This is like classic centric impact. All right, puck number 1 hitting puck number 2. That's pretty obvious. Eccentric, this happens more in reality, and because rigid bodies have crazy shapes, and you know, my coffee mug here's got a crazy shape, so where's its center of mass? I don't even probably really know. But if I threw this against the wall, it's probably not going to end up with the center of mass on the line of impact. One example might be like, let's say we have some box. Right? Box. All right. Here's the center of gravity of the box. So this is G with a sub B. And maybe that's being struck by a pendulum. All right, so here's some pendulum that's coming down, and here it's striking this box. All right, A+ on my artistry. The pendulum's going to have a center of gravity of, I don't know, maybe right here. So let's call this G pendulum. And the line of impact of this particular guy is obviously like right about here. Okay, so here's line of impact. So pretty obvious to see that the centers of gravity of those two objects are not on the line of impact, all right? Because that pendulum is hitting that particular box at that location, and the centers of gravities of either one of those objects doesn't pass about that point, okay? So what's going to happen is this is going to end up wanting to like impart some motion here of this particular box, right? It's going to want to rotate in this with this angular velocity after it gets struck. And, you know, if this guy's coming in with, you know, some angular velocity 1, well, maybe it goes out with angular velocity 2. You know, who knows? It's complicated, right? It's eccentric, just like my personality. All right, complicated. All right, Perrier. So, centric versus eccentric. Centric, very simple, very easy to analyze. Eccentric, complicated. All right. The difference between this class and your particle dynamics class is that in your particle dynamics class, every single example was a centric example. So all particle collisions are centric. Oh boy. And that's because they have no volume. Their centers of mass are where they collide. That's kind of the definition of a particle. They don't have any volume. All right. So easier to analyze. All right. I'll say most rigid body collisions are not centric. All right, so in real life, in reality, most rigid body collisions are not centric. All right, here's my Perrier bottle. I'm not going to drop it because I don't want all the fizz to escape. But the idea is if I have my Perrier bottle here and I drop it onto the desk, bang, well, my center of gravity is not along that line of impact. It's going to be eccentric. So there's going to be some rotation of my Perrier bottle after I drop it. And I don't want to do that to my sweet, sweet Perrier bottle, okay? But that's generally the way the world works. You drop it, there's probably very little chance, statistically speaking, that whatever collision you're going to have in real life, you're going to have this centric collision, all right? So usually, impart rotation. To objects. All right. So that's the general idea there. Centric versus eccentric. Now, let's dive a little bit further on centric analysis because this will help us sort of inform some of the eccentric analysis. So this is going to kind of be a little bit review, but let's dive in on this a little bit. So central right? This central or the centric impact is classified even further. So all collisions can be classified as either centric or eccentric, like I just talked about. But then furthermore, centric impacts can be classified as either direct or oblique. Direct centric impact is like what I drew before with the hockey pucks. It all has to do with the velocity of the center of gravity of the object. And for direct central impact, the velocity is along the line of impact. All right, our example. Puck number 1, puck number 2. They're colliding along this line here. Here's the line of impact. For direct central impact, they're running right into each other. Their velocities are along the line of impact. All right, great. Oblique, velocity not along line of impact. That might be this sort of situation where you've got a puck here and a puck here that are colliding with each other. Okay, but now they're not moving right at each other. Let's say one puck is moving up and one puck is moving to the left. So in this situation, this guy might be moving upward. This guy might be moving to the left. Bam! Their line of impact is still the same, right? So here is still their line of impact. It's a normal to the point of collision, right? And we see in this situation that they're going to hit each other, bang, and then maybe kind of like collide and move in that general direction. All right, so here the velocities are not along that line of impact. It's this like oblique impact. But you'll notice that the velocities in moving along the center of gravity, that the line of impact is still aligned with the center of gravity for these particular pucks, which is interesting. Okay, let's look a little bit more at this oblique impact because it is the more complicated of the two, and it informs information about direct impact. So if we solve stuff about oblique impact, then we can easily apply it to direct impact. So oblique impact. When we're doing analysis for oblique impact, we're going to do this conservation of momentum. Specifically, we're going to look at conservation of linear momentum. And we can look at it from like a system level, meaning we're looking at the two different objects kind of together, or we could look at it at an individual level where we look at a conservation for each one of the individual particles. All right, let's first look at it for the system as a whole. All right. So for the system as a whole, when we do this conservation of linear momentum, we draw the initial momentum, the impact, the final momentum. All right, so just like we did before, we have this initial situation. Here's our hockey puck A. Here's our hockey puck B. Got any hockey fans out there? Does anybody even like watch hockey anymore? I think like in Wisconsin, it's kind of a common thing. Wisconsin, Minnesota, like I think people understand and watch hockey quite a bit. Even like Chicago, like God, the Blackhawks have been great for the last decade. So hopefully there's some hockey fans out there. If not, then maybe these are soccer balls. I don't know. I know we got some ladies on the soccer team in the audience. Maybe think about soccer balls. Those have rotation. Better to think about hockey pucks. All right. Here's our line of action. Line of impact, line of action. And here, let's say we're coming in with random linear momentum. So here, this is MVA object 1. I know I've kind of drawn this before, but here we're going to draw it for this oblique impact, which we haven't really done yet. And so here, this is MVA. Sorry, this is B. One. All right, so this is situation 1, this initial momentum that we have. All right. Then we have impact, or our impulses. And what we'll see here is like nothing. All right. Yes, there's this collision point, but there's no vectors really to draw here. All right. The forces that are acting between these 2 points, typically we would draw our impulsive forces here. The forces that are acting between these 2 points are contained within that impact. Okay, so it's all internal forces here, and we don't draw these internal forces when we're doing this impulse or this impact. All right. Then after they've sort of hit each other, they ricochet. And maybe now we're leaving the scene of the crime. With here, what is MVA 2, and here this is MVB2. All right, so this is looking at it at like a system level. All right. For this system, momentum has to be conserved. All right, so that's one thing that we're going to enforce. Another thing that we're going to enforce is conservation of energy through a coefficient of restitution, which we'll talk about in just a second. All right. But to do this analysis, it's annoying to do it in traditional X, Y coordinates. All right. So what I'm going to say is easy to define, or we need a more convenient, let's say more convenient. Coordinate system. Okay. Here we'll assign unit vectors along line of impact. Usually we denote the unit vector along the line of impact as E hat n. So if I'm looking at this particular problem, that unit vector along the line of impact is going to be here. This is E hat n. Right. To define vectors in 2 dimensions, we need 2 unit vectors, okay? And then we'll need another one. So the unit vector along the line of impact is E hat n, and unit vector in tangential direction we call that E hat t. All right, so there's your E hat n. It's a unit vector in the normal direction. So this is along the line of impact. We're going to have also 90 degrees from that, a unit vector in the tangential direction, just E hat t. All right, hopefully we have all seen these definitions before. This should sort of jog memories. You may have seen it as lambda n and lambda t, or lambda hat n, although that's not as common. And lambda hat t, those two are pretty uncommon. But hopefully E hat n and E hat t, I think that's by far the most common. And this is what I'll sort of use in this class. Right? So with these unit vectors, you can resolve the linear momentum components not into xy now, but into E hat n and E hat t. Right? So can resolve velocities to E hat n and E hat t. So like the velocity of puck A in situation number 1 is something like the velocity of A in the normal direction for situation number 1 in E hat n. I mean, it's kind of a lot of subscripts here, but you get the general idea, plus the velocity of point A in the tangential direction, situation number 1, E hat t. All right, so it's just like resolving these guys into the various directions. You could do the same for velocity of B in state number 1, velocity of A in state number 2, and the velocity of B in state number 2. So I'll just write here, etc. All right. So you then apply conservation of linear momentum to system in E hat n and E hat t directions. All right. So here's our initial impulse final momentum diagram. We're going to apply conservation of linear momentum to this particular guy in the same way that we applied conservation of linear momentum to like the bullet problem or the box sliding and tipping problem. All right, it's the same general idea. Okay, I'm not going to go through that whole derivation. I'm just going to kind of like cut to the chase here and sort of maybe I'll draw it out a little bit. I got a little time, so let's talk about it a little bit more. So we apply conservation of linear momentum to the system in E hat n and E hat t. All right, so let's first look at individual pucks. And let's look, for instance, at like puck A. Well, puck A, for this particular example, is going to come in. Here we are. And we've got E hat n and E hat t. And this guy's coming in with, up here, we're going to resolve this velocity at A into E hat n and E hat t. So let's say it's coming in with some amount of velocity in the n direction, some amount of, I'll say momentum, I don't want to just say velocity, in the t direction. So here this is V, A, situation number 1, tangential direction. Here this is V, A, situation number 1, normal direction. So this is after resolving our vector into the various directions. Okay, this is how this is going to kind of go. So here's my initial. My impulses. Well, like I said, if we're just looking at the one puck by itself, then there will be an impulsive external force from the other puck that hits it. So the impulse that's going to be here, and this is going to solely be along what is E hat n. You're going to have some force that's transferred to this guy from the other puck. Right? We'll make a note here that since no friction between pucks, force is only in n direction. All right. So we're only going to have this impulsive force of puck B hitting puck A in the direction of the line of impact. All right. Final momentum. All right. We're going to have still, what here is VA2 T. And now maybe in the normal direction, because of the impulsive force of the other puck hitting it, maybe it bounces back the other direction. Maybe. I don't know. It's up to the math to make us decide. Right. Pretend these are perpendicular to each other. They should be. Okay, sorry about that. All right. So that's the general idea here. Okay, you can apply conservation of linear momentum in both directions. All right, so if you apply in the tangential direction, because there are only forces that are transferred between the puck at the point of impact, the only impulses that occur here are in the n hat direction. So because of that, if you apply conservation of linear momentum in E hat t, you're going to end up with the following results. That the velocity of A, situation number 1, in the tangential direction is equal to the velocity of point A, state number 2, in the tangential direction. And that's because there's nothing in the tangential direction to interrupt the momentum. There are no impulses that occur in the tangential direction because forces are only transferred between the pucks in the normal direction. All right. So tangential direction conserved. All right. So here's kind of equation number 1 that we have to work with. I'll also write here, same for puck B, and then mathematically that is the velocity of puck B, state number 1 in the tangential direction, is the same as the velocity of puck B, state number 2 in the tangential direction. Let's call this equation number 2. So when we apply our conservation of linear momentum, because there's no impulses, the tangential velocity is conserved. All right. Hopefully that's manageable and that's sort of easy to understand. So those are 2 equations that we have that will prove to be useful in our analysis later, even for rigid bodies. I know we're kind of talking about particles right now, but this will also be useful for rigid bodies, and we will see why in short time. All right. Next thing I want to do is I want to apply total conservation of momentum in E hat n. Right. So I'm going to go all the way back up to this general system here, which contains both pucks, and apply conservation of momentum in the E hat n direction. All right. So if we do that, then in E hat n, we have the following. That is the mass of puck A times the velocity of puck A in state number 1, strictly in the normal direction, plus the mass of B times the velocity of B, state number 1, strictly in the normal direction, plus there are no impulses. Okay, so this is like the total linear momentum of the situation in state number 1. Okay, linear momentum of puck A, linear momentum of puck B in state number 1, plus the impulses that occur for the system in state when they're together as a unit. All right, so we just wrote these two components, normal direction. Here, because we're looking at the system, the forces are internal to the system, right? So we do not include any internal impulses, okay? So here this is plus 0. Here, no external impulses. This is going to be equal to the momentum that we have in state 2, which will be something like the mass of the puck times the velocity of the puck, state number 2, in the normal direction, plus mass of the puck B times the velocity of the puck B, state number 2, normal direction. All right. So this equation is also one that we're going to use quite a bit in our analysis. Okay, so let's call this equation number 3. And this will be one that we frequently use in our impact analysis. Last thing we have to talk about, and this one is not something I can sort of quickly discuss, and that is conservation of energy. When two objects collide, momentum will be conserved. We've just talked about that. Conservation of momentum in the tangential direction means that the velocities of each of the individual pieces in the tangential direction will be the same going in as they are coming out. Great. Conservation of momentum in the normal direction tells us that for the system as a whole, the linear momentum of the system as a whole in the normal direction has to be the same going as it is coming out. Fantastic. The only thing that we have to worry about is the energy loss associated with the two particles hitting each other. Okay, think about two pool balls that hit each other when you're playing pool. What happens? Well, you hear a noise, bang. All right, that noise is energy. All right, that noise has to come from somewhere. Okay, so there's energy that's lost when two pool balls hit each other from just the noise that they make. Okay, all right, when those two things hit each other and create heat, hit each other, they also create heat. All right, that heat has to come from somewhere. That heat is energy that's lost from that collision. Okay, so when it comes to conserving energy when two things collide with each other, energy is not necessarily always conserved in the system. So when you write something like the kinetic energy of object number 1 plus the kinetic energy of object number 2 must be conserved through the system, that doesn't apply here because there's lots of energy that's lost when two things hit each other through things like heat and sound and just viscoelastic nature of the materials, which is kind of a complicated topic, but is the general idea. So I'll write this more explicitly as when objects collide, they lose energy. I don't want to say lose energy, but not all of the energy that goes into the velocities coming in comes out. You might lose energy to heat, or sound or viscoelastic behavior, etc. Other things. What do I mean by viscoelastic behavior? Okay, well, have you ever used silly putty? All right, silly putty, if I drop it from here onto the ground, it's just going to stick to the ground. Okay, it's not going to rebound back in any way. All right, that's because it deforms to absorb the energy of the impact. It's this viscoelastic sort of character to it. That's a lot different than a bouncy ball. All right, if I drop a bouncy ball from here and it bounces off the ground, it's going to come back to almost the same height which I dropped it from if it's a good bouncy ball. All right, the way that we measure how much energy is lost from an impact is with a constant known as the coefficient of restitution. Okay, the coefficient of restitution is usually given the variable little e. Got a lot of e's running around today. We had e hat t, e hat n, coefficient of restitution, which is little e, all this sort of stuff. All right. So if e is equal to 1, we call this a perfectly elastic collision. And in this situation, no energy is lost. Right? So no energy is lost to outside sources. No heat, no sound, no viscoelastic deformation. Perfectly elastic collision. All right? All right. The opposite of that is if E is equal to 0. This means that there is no rebound from one object to the next, meaning that one guy hits the other and they stick together. All right. It's just like the bullet problem. When the bullet hits the plate and we said that it embeds into the plate, that is a perfectly plastic collision. All right. The momentum associated with that bullet gets embedded into the plate. There is no rebound. All right. This is perfectly plastic. All right. Reminds me of Mean Girls. The plastics. All right. Energy not conserved. All right. Object 1 sticks to object 2, or object A sticks to object B. Since we're talking about, yeah, let's do that since we've been talking about that. Object A sticks to object B. All right. There's a long derivation for how to come upon the coefficient of restitution, which I just don't have time to do right now. It has to do with the impulsive forces that occur between the puck at A and the puck at B and balancing the energy associated with those impulsive forces. It's complicated. I'll cut to the chase and say that how we're going to apply it here is to say that in the normal direction, the velocities are balanced by this coefficient of restitution. Mathematically, the coefficient defined as when two objects collide with each other, we define this as the velocity of object B, state number 2, in the normal direction, minus the velocity of object A, state number 2, in the normal direction, is equal to my coefficient of restitution multiplied by the velocity of object A, state number 1, in the normal direction, minus the velocity of object B, state number 1, normal direction. That is your coefficient of restitution equation. All right. This here is equation number 4. So we have these 4 equations now that are available for us to work with when we're talking about impact. They come from various sources. Number 4 comes from conservation of energy. Number 3 comes from conservation of momentum of the system. And numbers 1 and 2 came from conservation of momentum in the tangential direction. Okay, that's it for today. We'll apply these equations to a rigid body impact problem tomorrow. Thank you for coming. Sorry I kept you 1 minute late.